All right, so we're going to pick up where we left off from the previous lecture. If you remember that the general solution to the heat equation is given by a convolution of the fundamental solution with your initial condition here, where we're talking about solving the following Cauchy problem in 1D, right? So with the initial condition g of x defined on R, and g is going to be continuous, and U satisfies the heat equation, okay? Now, let's extend to, like we did in wave equations, the quarter plane problem, where essentially we want to solve U sub t equals kuxx, where x is greater than 0. And so now we're going to have a boundary condition in addition to our initial condition. Well, let's start off with it just being a homogeneous Dirichlet boundary condition, okay? Just depends on the concentration or the heat level at the boundary. This would be like you have some boundary of a rod, and you're fixing the temperature of the rod there. So maybe you have some heating element here, okay, that is fixing U0 of t to be 0, I guess, and then x here, radiates outward. So you want to see how the propagation of the initial condition by diffusion interacts with this 0 fixed boundary. Okay. So the way to solve this equation is not so different than the approaches that we talked about in the case of the wave equation. The idea is to use what's called odd extension. An odd extension, we're going to take the initial condition and just reflect it across the boundary, okay? So let's say that, g of x, well, let me rewrite this a bit so that I have room here. Let's say that g of x, right, is just some function like this, okay? Then if we odd extend it across the boundary, we're going to get some reflected shape of it like that, okay? And so in the process, we've turned it into a problem on one dimension that covers the entire line, right? So now g tilde of x is defined on x and R, okay? And why is this okay? Well, because in actuality, in our problem, we are not interested in anything where x is less than 0. So as long as the solution on x greater than 0 satisfies our initial condition, our boundary condition, and our PDE, okay, then everything works out, right? In actuality, everything that's going on here is not relevant to our problem, okay? But we can bring the extended domain in essentially to allow us to use the techniques that we used before, okay? So now U of xt is just going to be our initial condition that's been extended convolved against our fundamental solution, okay? Now, we want to make sure that this worked, okay? And in particular, we need that the limit as x goes to 0 from above of g of x is equal to 0, okay? So if we want, sort of nice continuity and everything, then we need this additional condition now, Otherwise, our g tilde is not going to be continuous. So that's why it has to cross through 0 at 0 here, okay? So that's the only other thing that comes into play here. Otherwise, this is just looking precisely like our general solution from before, right? First of all, we know that use sub t equals k uxx because this is just going to be the general solution where g of x is continuous, okay, if g is continuous and we have this additional condition here, okay? So as long as g of x goes to 0, as x goes to 0 from above, okay? So that works fine, okay? Also, u of x 0 is equal to g tilde of x. It's just going to be equal to x as long as x is greater than 0, right? Because, right, the sine function, or some people call this the signum function, is just going to be 1 and minus 1, depending on, and then it's going to be 0, right? Depending on whether x is greater than 0, x is less than 0, or x is just equal to 0, right? So even though this is piecewise continuous function, because g vanishes at 0, everything is fine, okay? Now, the next property of the solution that we need to check is just that u of 0t is equal to, sorry, I need to move something out of the way here. Is just that essentially our boundary condition is satisfied. Excuse me. Okay, so we have, what's u0 of t? Well, that's going to be phi of minus yt g tilde of y dy. Okay, this is 0 basically because of evenness of phi, okay, and oddness of g tilde, right? How do we know that this is even, right? Well, it's basically, you know, a bunch of constants in t e to the minus y squared over 4kt, right? So if I plug in plus or minus y there, right, I get back the same answer, right? That times an odd function gives me an odd function. When I integrate an odd function over the real domain, I get 0, okay? So that's why we enforced oddness with respect to g tilde, okay? And so then lastly, I write out u of xt, right? I can see that, well, this is going to be equal to, if I split it up now, the integral from 0 to infinity of phi x minus y t g of y dy plus the integral from minus infinity up to 0 of phi of x minus y t minus g of y, of minus y, excuse me, dy, right? And so then that can be written through a change of variables and a recombination as phi of x minus y t gy, okay? Then I have this minus sign coming through, right? And if I change variables, if I flip y to be minus y, then I'm integrating from 0 to infinity, okay? And I end up with phi of x plus y t times g of y dy, okay? Or in other words, just the integral from 0 to infinity, phi of x minus y t minus phi of x plus y t multiplied by g of y dy, okay? So again, we can double check this, right? So the limit as x goes to 0 from above, u of x t in this case, right? It's just going to be the integral from 0 to infinity of phi of minus yt minus phi of yt, okay? But then because of the evenness of these, they're going to cancel each other out and we get 0, okay? So indeed, our boundary condition is satisfied, okay? So that's why we use odd reflection in this case. And this is sort of foreshadowing a little bit what we're going to do in the case of Green's functions when we get to elliptic equations. Essentially, what we've constructed here is really a Green's function for the bounded domain that goes from t greater than 0 and x greater than 0, and given a Dirichlet boundary condition. Okay, we're going to circle back to this idea of odd reflection when we start talking about Green's functions again later in the course. Okay, for now, we just know that when we have a Dirichlet boundary condition in the context of the heat equation, we want to use odd reflection. In the case of ux0t is equal to 0, instead, we would like to use even reflection. So in a sense, then, it's as if we took our initial condition and even reflected it across the position x equals 0, okay? So that is our solution in this case, right? Our solution in the odd reflecting case, right, is this one. So this is in the case where u of 0t equals 0, okay? This, just to separate these out, is in the case where u sub x 0t equals 0, okay? And you can check on your own that this satisfies our PDE in that case. Our PDE in that case would be ut equals k uxx, ux 0t is equal to 0, non t is greater than 0, and ux0 is equal to g for x greater than 0. So again, we have, this positive domain, right? So x and t just are both greater than 0. Okay. That is the method for quarter plane problems. You'll have a chance to practice that on your homework. Let's move now to methods for proving uniqueness in the case of the heat equation, okay? So remember that what we have is that solutions in general, right, to the heat equation are given by this convolution of the fundamental solution with our initial condition, okay? The properties of the solution that we have are this infinite propagation speed, which is unphysical. It follows Fick's law of diffusion, excuse me. And we have this smoothing property of the heat equation that occurs as we move away from t equals 0, right? So just to summarize that, right? What do we know so far? Okay, we know that that the general solution to u sub t equals k uxx, right? For x is in R and t is greater than 0, u of x 0 equals g of x for x is in R is given by u is equal to the integral from minus infinity to infinity of phi of x minus y t g of y dy, okay? On x greater than 0, right, if we have a Dirichlet BC, in other words, if we have that u of 0t is equal to 0, okay, then u of xt is equal to the integral from 0 to infinity of phi of x minus yt minus phi of x plus t, x plus yt, g of y dy. And for what's called the Neumann boundary condition, right, or in other words, ux 0t equals 0, we have that u is equal to the integral from 0 to infinity of phi of x minus yt plus phi of x plus yt, g of y dy, okay? Properties of these solutions, okay, are this infinite propagation speed, okay? And remember, this is on physical, and we talked a little bit about why in the last lecture, okay? These solutions, they satisfy what's called Fick's law, which essentially states that the flux of heat or substance should move down the gradient, okay? And essentially this is a continuum approximation to the discrete exchange of either molecules in the case of diffusion or heat, right? We also have smoothing property so that u of x0, even if this is R, and let's say that it's bounded, right? This is going to imply that u of xt away from 0 is going to be C infinity and still bounded, right? This is basically for any p greater than 0, okay? So we have a solution. We have different situations where we can get that solution. We know that it's infinitely smooth. That's going to be helpful.